Hello APC Mechanics students in Unit 3 Work Energy and Power, Class 9, Conservation of Energy, Part 3. In today's video, we're gonna solve some exercises related to what we have explained so far. Exercise 1, a 2 kg object is released from rest from a height of 3 meters above Earth's surface. How much kinetic energy does the object have when it reaches a height of 1 meter? Now at this point, we can solve the exercise in several ways. One way to do that is using conservation of energy, for example. Then let's start by doing a small sketch. This is the ground. Initially the object was at point A, that is 3 meters above the ground. And the speed at the point A is 0 simply because they have mentioned it's released from rest. And it will fall down to point B such that B is at a height of 1 meter above the ground. Then we need to find the kinetic energy at the point B, and this can be done by considering the conservation of energy, since here we assume that frictional forces are neglected. Then the energy at A equals to energy at B, and remember that if this is apart from a free response, we need to state that, apply conservation of energy. At A we have kinetic energy and the gravitational potential energy, and at B we have kinetic energy and gravitational potential energy. Notice that I didn't include the potential energy of the spring since we don't have a spring. Now kinetic at A would be 0 because it's released from rest. We are interested in determining kinetic energy at B, and that would be the mass, which is 2. So this is mgh multiplied by g. So here the number seems to be perfect. Let's consider g to be 10, and h would be 3, equals to the kinetic energy at point B plus 2 multiplied by 10 multiplied by the height. Here I'm considering this is the PE level, which is the lowest point in my system, multiplied by 1. So that would be 60 minus 20, and that would be 40. Then the kinetic energy at the point B would be given by 40 joules, and the correct choice is E. However, another way to do that is to utilize that the kinetic energy is given by half mv square, and the speed upon reaching the point B, because it's released from rest, is given by radical 2gh. Then in this case v square would be given by 2 multiplied by 10 multiplied by h, which is, so h would be the descending height, which is 2, and that would be 40 joules. Sorry, 40. Here in this case this is v squared, and the unit is given by meter square per second square. Then that would be half multiplied by 2 multiplied by 40, and that would give us also 40 joules. Exercise 2. A disk of mass m slides with negligible friction along a flat surface with a velocity v. The disk strikes a wall head-on and bounces back in the opposite direction with the kinetic energy 1/4 of its initial kinetic energy. So whenever they're talking about factor, then we're interested in the factor of change. Now let's do a sketch. This is the disk that is sliding, and it will hit a wall. Then after hitting the wall, it will slide back in the other direction. And remember, be careful here that they're asking about the velocity, and velocity is a vector quantity in which we're interested in directions. Now, since we are interested in velocity, then let me say that the kinetic energy would be half mv square, and let's isolate for v. Then this is down, we will take it up, and this is up, we will take it down. Then v would be given by the square root of the double of the kinetic energy divided by the inertia. And now we're ready to do the factor of change. Then 2 didn't change, that would be replaced by 1. The kinetic energy is changed by a factor 1/4, and it's the same object, so the mass remains unchanged, and that would be the radical 1/4, which is half. Now in this case, both either B or D are correct. Initially, if it's moving to the right before it hits the wall, because they mentioned the velocity v, which means that the initial direction is positive, so this is positive. After it strikes the wall, the velocity will change by a factor of half, but we need to take into consideration that there is change in direction. Then D would be the correct choice. Exercise 3. This exercise is very important. A 2 kg block is attached to a string that passes over a pulley and is attached to an ideal spring of constant K is 100 Newton per meter. We have the mass, we have the stiffness of the spring. The pulley and the string have negligible mass, and there is negligible friction in the pulley. So basically we're assuming that the pulley is ideal which means the tension here is perfectly transmitted here. The block is held in place with the spring at its original unstretched length and then released from rest. So here let's be careful. Initially at the point A, which is the point A here, the initial speed is 0 because it's released from rest, and we don't have elastic potential energy because the spring is unstretched. The amplitude of the resulting oscillation is most nearly. Now, what is meant by the amplitude? Let me explain it here. Suppose we have a block with a spring that forms an horizontal oscillator. So this is the equilibrium position. Now, after the block has been set into oscillations, the block will oscillate left and right between two extreme positions. The amplitude would be the distance measured for half the distance, which is this one, and not the complete distance from two extreme positions. So if you're asked about the amplitude would be the distance traveled from one extreme position to the equilibrium position. Okay, so basically that would be the amplitude and not the distance between the two equilibrium positions. Now, why this is important? Let me say that this is the point A. At the point A, we have 0 speed and the elastic potential energy is given by 0. Now what's gonna happen here, after we release the block from rest, the block will oscillate up and down. So let me here draw another figure. Now the spring, we can consider that the spring, since the tension is transmitted equally, we can consider the spring is attached to this part, or you can also ignore this fact. Let me do a drawing here. So this is the block. Now after we release the block, we will expect that the block will fall a certain distance. So this is the point A and this is the point B, and if we assume that there is no friction, the block will oscillate between points A and B. Now the equilibrium position would be half the distance from the point A to the point B. Then if we're able to determine the distance from the point A to the point B, then the amplitude of oscillations will be half of that distance. Why? Because as we have explained here previously, the equilibrium position is half the distance between the two extreme positions. Now, how can we determine the distance from the point A to the point B? This can be done using conservation of energy. Then let me say energy at A equals to the energy at B, and remember that if this is apart from a free response, we need to say apply conservation of energy. Then at the point A, we have kinetic energy, we have gravitational potential energy, and we have the elastic potential energy of the spring, which is equal to the kinetic energy at the point B plus the gravitational energy at the point B plus the elastic potential energy of the spring at the point B. Okay, since they mentioned it's an ideal spring, then the elastic potential energy is given by quadratic term half kx squared. Now initially, because we have released the block from the point A with no speed, then kinetic energy at A would be 0. Now I will consider that this level to be the PE level, which is the lowest point in my system, which means that the gravitational potential energy at the point B would be 0. Now at the point A, we have a gravitational potential energy which is given by mgh, plus because the spring at the point A, it's neither compressed nor elongated, then I will consider the elastic potential energy at the point A to be 0. Now at the point B, when it reaches the other extreme position, we know that the block at this point will change direction and will go up. So the speed at this point will momentarily vanish because it's an extreme position, so that would be 0 as well, plus 0 plus the elastic potential energy stored in the spring, which is given by half kx squared. Now here notice carefully, if h represents the height from the block A to the PE level, now because the block descends a vertical height h and the string is connected to the spring, then the spring will elongate by the same distance x. So what I'm trying to say here is that h would be exactly the same as x. So we can say that h equals to x. Now in this case, mgx is given by half kx squared. Now power 2 cancels with the x. then mg is given by half kx, and if we isolate for x, then x is given by the double of mg divided by k. That would be the double of 2 multiplied by 10, because number seems to be perfect, divided by 100. That would be 40 divided by 100, which is given by 0.4 meters, which is eventually given by 40 centimeters. But remember that this is not the correct choice. This is the distance between the two extreme positions as the block is oscillating vertically up and down. If we need the amplitude of oscillations, we need to divide this by 2. Then 40 divided by 2, that would give us 20 centimeters, and the correct answer in this case would be D. Now, exercise 4. A block slides from rest with negligible friction down the track above, descending a vertical height of 0.5 meters to point B at the bottom. It then slides on the horizontal surface. The coefficient of friction between the block and the horizontal surface is 0.2. How far does the block slide on the horizontal surface before it comes to rest? Now, first of all, at the point P, we can directly determine the speed of the block since we know the height, and the speed would be given by V is the radical of 2gh, which is the radical of 2, number seems to be perfect, and h is given by 5, and that would be 10 meters per second. So we know the speed at the point P. Since we know the speed at the point P and the final point, let me say the point Q, would become to rest, then the final speed is 0. Then we can directly determine how far does the block travels from P to Q using different methods. My approach would be the work energy theorem, which states that the variation in the kinetic energy is equal to the work done by all the external forces. We're talking about the final kinetic energy, which is 0, minus the initial kinetic energy, which is accessible because we know the speed, which is equal to the work done by the different forces acting on the block, given by the pull of gravity, normal push, and given by friction. Eventually this is 0 and this is 0 because they are perpendicular to the displacement, which is horizontal. That would be minus half mv square initial, which is at the point P, and this is equal to the work done by the friction, which is minus F multiplied by D. The friction is given by mu K, mg, and D would be the distance traveled, which is how far that we are interested in calculating. That would be minus mu K mg multiplied by the distance, and we're interested in determining the distance. Notice that inertia is not given because simply it cancels. The minus sign cancels out. That would be half v square at the point P divided by mu k and g, and that would be equal to the distance d, which corresponds for how far. Now half multiplied by 10 divided by 0.2, and so this is square multiplied by 10. Now plugging that on the calculator, we're gonna get a value of 25 meters, which makes E to be the correct answer. Now exercise 5. Two identical massless springs are hung from a horizontal support. A block of mass 1.2 kg is suspended from the pair of springs as shown above. When the parallel block is in equilibrium, each spring is stretched an additional 0.15 meters. The force constant of each spring is most nearly. Now this is a bit tricky. Why? Because they're asking for the force constant, which is K, not of the springs combined, but for each spring. And we know that whenever springs are in parallel, the stiffness is additive, which means K equivalent is equal to K1 plus K2. If we're assuming that both strings are identical, then that would be 2K. So basically, if we determine the equivalent stiffness, we would be able to deduce K. Notice that here the springs are identical. Then let's draw an FBD. What are the forces acting on the 1.2 kg block? We have the pull of gravity down. We have the tension. If these are modeled by a single spring, that would be the tension up. So when the block is in equilibrium, which means that these forces are balanced, then we can say the tension is equal to the pull of gravity. Here we didn't discuss the types of the springs, so we're going to assume that they are linear, which means Kx. This K would represent the equivalent stiffness. So let me write it perfectly. K equivalent multiplied by X is equal to M multiplied by G. Then the equivalent stiffness is given by the mass, which is 1.2, multiplied by G, number seems to be perfect, and divided by X, which is 0.15. Now plugging that on the calculator, we're gonna have a stiffness of 80 newtons per meter, which means that in order to elongate or compress both the springs by 1 meter, we need to exert a force worth of 80 newtons. Now we're interested in determining the force constant of each spring and not the equivalent. Then because these are in parallel, then K equivalent would be the first spring plus the second spring, knowing that they are identical. Then the equivalent stiffness is given by the double of the stiffness of each spring. Then K is given by 80 divided by 2, and that would be 40 newtons per meter, which makes A to be the correct answer. Exercise 6. The above graph represents a hypothetical potential energy curve for a particle of mass m if the particle is released from rest at position r0. Then let me say this is the point A, and this is the point B. The speed at the point A is 0. Then we need to find the speed at the position of double r0. Then this can be done using the conservation of energy. Energy at A is equal to energy at B. Now energy at A is given by kinetic and gravitational potential energy. Here no need to worry about springs because we don't have springs. Kinetic energy at B plus gravitational potential energy at B. At A that would be 0. Now what about UGA? By referring to the point A, we can know that it's given by 3u0. It's given by half mv square at the point B that we're interested in calculating, plus the gravitational potential energy at point B, which is given by u0, which means that the double of u0 is given by half mv square B. Then v square B is given by 4 multiplied by u0 divided by m, which means the speed at the point B is given by the square root of 4u0 divided by m, which makes C to be the correct answer. Now exercise 7. Cart A is traveling east when it collides with cart B, which is traveling north. Cart A has a mass of 3.05 kg and cart B has a mass of 2.10 kg. The two carts travel together as a single object on a horizontal surface at an angle theta relative to due east, as shown on above. In another trial, the speed of the carts immediately after the collision is 0.60 meter per second, and the cart slides 0.24 meters on the horizontal surface before coming to rest. Now here what they're saying is that this is a top view. Carts A and B are traveling on a horizontal surface. They will collide at this point, and after this point they will move as a single object. So this is A and B combined, of a mass 3.05 kg plus 2.10 kg. They will travel together a distance of 0.24 meters. And the speed at this point directly after the collision, let me say this is the point C. At the point C, the speed of the system is given by 0.60 meters per second. And now we're interested in determining the coefficient of kinetic friction. We know that this is accessible using the work energy theorem, but remember that if this is a free response, we need to say apply work energy theorem is equal to the work done by all the external forces. Kinetic energy final would be 0 because the system would come to rest, minus the initial kinetic energy is equal to the work done by the different forces, gravity, normal push, and the friction. And remember that if this is horizontal, that would be 0. That would be 0 for the same reason that we talked about previously, minus half the mass of the system combined ma plus mb square is given by minus the work done by the friction, which is minus F times D. Friction is mu k Fn because it's horizontal, there is no modification on mg. That would be minus mu k multiplied by the combined mass multiplied by g multiplied by the distance t which is traveled. Masses cancels perfectly. This should be v square. The minus sign cancels as well. Then that would be half v square is given by mu k g multiplied by d, and we're interested in finding mu k. Mu k would be half v square divided by gd, which is half, and the value of v is given by 0.6 to the power of 2. Now G, let's assume it's 9.81, and the value of D is given by 0.24. Now plugging that on the calculator, we're gonna have a value of 0.08, which makes A to be the correct answer. It's almost close to 0.08. I think it's 0.07 something. Now exercise 8, blocks A and B, each of mass m, are connected by string that extends over a pulley. Block A slides on a horizontal surface and block B is on a surface that is inclined at an angle theta above the horizontal as shown. Both surfaces have negligible friction. Frictional forces are neglected, which means we can use conservation of energy. The masses of the string and the pulley are negligible, and the pulley rotates with negligible friction, so we can use conservation of energy. The system is released from rest. Then the initial speed for both blocks is 0, which the following is the correct expression for the speed of the block B when it has moved a distance x. Now we're talking about the speed of the system, whether we're talking about A or B. Both blocks admits the same speed because the string is inextensible. Now let me consider different points in my system. The first point, or initially, let me say we have initial point which is given by I, and the final point would be F after the block M has descended a certain distance along the ramp. Now because the string is inextensible, if block A moves a distance x, then block B will descend the same distance x. Then we will say apply conservation of energy. Energy final equals energy initial. Now what is energy? Energy is both kinetic and potential, but here notice that we don't have one body, we have two bodies, and we should include two kinetic energies, two gravitational energies for both final energy and initial energy. Then I would say kinetic energy A initial plus kinetic energy B initial is plus gravitational energy A initial plus gravitational energy B initial. That should be equal to kinetic energy A final plus kinetic energy B final plus the gravitational potential energy of A final plus the gravitational energy of B final. Initially we started from rest, which means this is 0 and this is 0. Now what is my PE level? Let me choose my lowest point to be the PE level after the block M has descended a distance x. So this is my PE level. Now here, if you notice carefully, if block A remains sliding on this horizontal surface, which means this cancels with this because they have the same value. Now this is B. Now what about the gravitational potential energy of the block B? That would be mg, and here I should place h, which is the vertical distance from the PE level, which is this distance. But we're interested in expressing h in terms of the distance that the block M travels along the ramp, and that would be x, and we know that h is given by x sine theta. So that would be x sine theta, which is equal to the final kinetic energy of A, that would be given by half mv square. And notice that here I didn't differentiate between the masses of A and B simply because they have each of mass m, and that would be plus half mv square plus 0, because as the block B moves down to the PE level to my choice, that would be 0, which means mg x sine theta. Now half with half would give us 1, that would be mv square. M with M, they would cancel, then the speed is given by the radical of g x sine theta, which makes B to be the correct answer. Exercise 9, the figure shows block with different masses hanging from a spring or combination of two springs. All the springs are ideal and have the same spring constants K. Which of the following correctly ranks the system in order of most stored elastic potential energy to when the spring system are stretched a distance d from their unstretched length? So basically we have three configurations of springs or combinations of springs. Let's assume that the springs are ideal as they have mentioned here. Then the elastic potential energy is given by half kx square. Then the elastic potential energy depends on two factors, on k and on x. It's quadratic in x and linear in k. However, since all of the three configurations are stretched by the same distance d, So X won't enter into the game. So the elastic potential energy depends only on K. Now let's recall these configurations. This is series and this is parallel. Let me say that this is 20 newtons per meter. So here we have two springs in series and here we have two springs in parallel. In parallel, we know that the stiffness is additive, and that would be given by 20 plus 20, and that would be given by 40 newtons per meter. So third configuration would be 40 newtons per meter. Now what about the series configuration? We need to add them using the reciprocal sum, which is 1 over K equivalent. That would be 1 over 20 plus 1 over 20, which makes it 1 over 10. Then 1 over K equivalent would be 1 over 10, which means K equivalent is given by 10 newtons per meter. So that would be 10 newtons per meter. Now numbers, my choice to be 20 newtons per meter, it's not important. We just need to do comparison between these two values. So upon adding springs in series, the stiffness decreases. Upon adding series in parallel, the stiffness will increase. So among these configurations, the highest stiffness would be 3, then comes 1, then comes 2, which makes the elastic potential energy at its most at 3, then at 1, then at 2, which makes E to be the correct answer. Now exercise 10, in the system of two blocks and a spring shown above, blocks 1 and 2 are connected by a string that passes over a pulley. The initially unstretched spring connects the block 1 to a rigid wall. Block 1 is released from rest, initially slides to the right, and is eventually brought to rest by the spring and by friction on the horizontal surface. Which of the following is true of the energy of the system during the process? Now they're telling you the total mechanical energy of the system is conserved. So we have a friction, which means energy is not conserved. We will exclude this. The total mechanical energy of the system increases. We know that this violates the principle of energy because energy is always the same or decrease. The energy lost to friction is equal to the gain in the potential energy gained by the spring. The potential energy lost by block 2 is less in magnitude. The potential energy lost by block 2 is greater in magnitude. Let me tell you here what's happening. They're interested in the potential energy, let me say, lost by block 2. Now here what's happening is that after we release the system from rest, block 2 will descend to a certain height, which makes block 2 loses gravitational potential energy, and this conversion will cause the elastic potential energy of the block 1 to increase. Now if there is no friction, then if this loss is minus 5 joules, then this gain would be plus 5 joules. However, because we're talking about friction, this is not the case. So if this loss is minus 5 joules, then this gain would be, for example, plus 4 joules, which makes the following statement correct. The potential energy lost by block 2 is greater in magnitude because there's a minus sign than the potential energy gained by the spring, which makes E to be the correct answer. Now exercise 11, which is an exit ticket for today's video. A 2 kg block is attached to a horizontal ideal spring. Ideal, which means we can use the fact that US is half kx squared. With a spring constant K is given by 100 newtons per meter. The block spring system is set on a horizontal surface with negligible friction. A graph of the potential energy U as function of time for the system is shown. The maximum displacement x max of the block from its equilibrium position and the maximum speed v max of the block during the motion represented by the graph are most nearly. So let's recall and say that the energy of the oscillator is given by E, given by K plus the elastic potential energy. Now we know that if there is no friction, as stated here, this means that this is conserved. Then there is a continuous internal exchange from K to US. So if this is 3, that would be 7 if the total is 10. If this is 5, that would be 5. If this is 4, that would be 6, so on and so forth. And more importantly, if this is 10, that would be 0. If this is 10, that would be 0. What I'm trying to say here is that when K is minimum, the elastic potential energy would be maximum. And so if this is 10, maximum, that would be 0. And if this is maximum, which is basically positive, which is 10, that would be 0 as well. Now we need to find the maximum position first. The maximum position can be determined from these points because the elastic potential energy is maximum and is given by 2, and the kinetic energy would be minimum, which is basically 0. The speed would be 0. Then U max is given by 2 joules, and we know that the max potential energy is given by half kx max square, which is equal to 2. X max square is given by 2 multiplied by 2, which is 4, divided by the stiffness, which is 100, and that would be 0.04 meters square, which means that the maximum position, the extreme position, is given by 0.2 meters, which is 20 centimeters, which makes directly C to be the correct answer. But let's double check by calculating the maximum speed. The maximum speed can be determined from the kinetic energy max, and because, as we've mentioned previously, the maximum kinetic energy would be 2 in this case, and that would be given by half mv square max is equal to 2. Now V max square, that would be 4 divided by the mass, which is 2, and that would be basically 2. Then V max would be the radical of 2, which is given by 1.41 almost meter per second, and indeed the maximum speed is given by that. Then that's it for me in this video, guys. See you soon in a new one.